Hi, we're going to look at solving this differential equation in this video. And so there are a couple things to notice. We have a second order linear differential equation, non-homogeneous, and the external forcing function is described by 9e to the negative t. So that would be a force that would be 9 at t equals 0 and then decrease exponentially approaching 0. But also we have an impulse at t equals pi over 2. So large magnitude, short duration is what that function models. Okay, so we're going to solve this just like we solve usually using Laplace transforms. And so I'm going to start by taking the Laplace transform of both sides of the equation and use my linearity property to separate that term by term and pull constants out front. Okay, so I've gone ahead and taken the Laplace transform of both sides of the equation, and I wrote down a couple of references here from our table of Laplace transforms that we've been using in class. So Laplace transform of e to the negative t, that's line 5 with a equals negative 1, and Laplace transform of our impulse function at pi over 2, that's line 21 with a equals pi over 2. All right, so next step, as usual, we're going to go ahead and substitute in our initial conditions. This one's kind of nice because they are both 0, so we've got all of those dropping out. And then the next thing I want to do is factor out my capital Y and solve for Y. Okay, and I went ahead and left my terms separate, just kind of thinking a couple steps ahead until I'm ready to do the inverse Laplace transform, because the behavior of whatever motion is described by our differential equation changes at t equals pi over 2. We should expect that we're going to have that unit step function in our answer stepping at pi over 2. And so you can probably see that's going to happen from taking the inverse Laplace transform of this last part here that has the e to the negative pi over 2s times some function of s. So I've kept things separate. The stuff that involves e to the negative pi over 2s separate from the terms that do not involve e to the negative pi over 2s. From here, I want to go ahead and prepare to do my inverse Laplace transform. So s squared plus 2s plus 10 does not factor easily, so I'm going to end up completing this square. For that, I will think about that s squared plus 2s plus 10 as s squared plus 2s plus 1 plus 9, separating that 10 into the 1 and the 9, so that the first three terms factor into s plus 1, the quantity squared, and then I have the 9 left over. So that's what I'm going to do with that term. With the first term here, I'm going to need to go ahead and do partial fractions and completing the square. It'll be easier if I do the partial fractions first and then deal with completing the square. Okay, so I went ahead and did the partial fractions. I didn't write out the work for using the augmented matrix to solve that system, but hopefully at this point that's pretty straightforward. So I'm going to go ahead and write out the equation that I have with my partial fractions broken apart. And I'm going to use my completed square form, the s plus 1, the quantity squared, plus 9, in place of the s squared plus 2s plus 10 on a couple of those denominators. Okay, so I've gone ahead and written my expressions here with my partial fraction decomposition and my completed squares on the denominators. We are almost ready to do the inverse Laplace transform. I do need to do just a little bit more manipulation on my two fractions that have the s plus 1 quantity squared plus 9 on the denominator. So what I'm looking for there is to look for my lines in that table of Laplace transforms that have a denominator of that form, s minus a, the quantity squared plus b squared, and then I need to force the numerator to be what I need. So I have two of them. I have one where the numerator is s minus a, and then I have another one where the numerator is b. So for the last one here, that I have a constant on the numerator there, so I want a 3 on the numerator there. That would be the b. And then I'm going to balance that on the first one where I have the denominator of s plus 1, the quantity squared plus 9. I want s plus 1 on the numerator. And fortunately, the algebra to get there is pretty straightforward. All I'm going to have to do this time is factor out a minus 1. Sometimes you might have more complicated algebra to do to make that happen. All right, so I'm now ready to apply the inverse Laplace transform to both sides of the equation. So I'm not going to write that out, but I will be using the linearity property to separate that term by term. And so then the key is just kind of keeping track of what I have in the table and what I'm doing. And the tricky one is going to be this last term here, where I'm going to need to use line 20 on that table of Laplace transforms. And the tricky thing will be remembering to do the shifts. All right, so on this last term here, I'm going to look up the inverse Laplace transform of 3 over s plus 1, the quantity squared plus 9. So that is line number 8 with a equals -1 and b equals 3. And so I get that the f of t function there is e to the negative t sine of 3t. But the shift, that's the tricky part, is remember when you do that inverse Laplace transform using line 20, which is what I'm using overall here, I need to shift that so that I have f of t minus pi over 2. So what I'm going to actually have here in my answer is that f, but shifted pi over 2 units to the right. Okay, and there are a couple places to be careful here. You want to be careful with your minus sign here. So I have e to the negative t, and then when I put t minus pi over 2 in place of t, I've got that minus sign that has to apply to all of that. And then the same thing in the trig function. When I put my t minus pi over 2 in that trig function, I need to make sure that both the sign and the 3 apply to the entire t minus pi over 2. All right, at that point, I have my answer. Occasionally, if you look at answers somewhere else, you'll maybe notice that they use some algebra to simplify some of what I have here at the end. You could distribute through the minus sign in the exponential function. You could distribute through the 3 in the trig function. You could also use a trig identity to rewrite that. It's not necessary to do that simplification. So that's kind of optional. What you might want to be able to do though too is if you are asked to graph the solution, which this problem asks us to do, is be sure that you're clear about what that unit step function is and what it means in terms of the solution. So here I will have when t is less than pi over 2, the unit step function will output 0. So I'll have e to the negative t minus e to the negative t cosine 3t, and the rest will be 0. And then at t equals pi over 2, and afterward, that unit step function will output 1. So I'll have the first few terms that were there that weren't times that unit step function, and then 1/3 times 1 times e to the negative t minus pi over 2 times sine of, I'm going to go ahead and distribute through my 3 here, 3t minus 3 pi over 2, where t is greater than or equal to pi over 2. All right, so there is my solution written in piecewise form. So either what I had on the line above, where it's written with the u function, or what I have in this line where it's written as a piecewise function, either way is fine. All right, I've gone ahead and graphed this on Desmos, so I'm going to pull that up. Okay, so you can see here I've got y equals, and then I've got the part of my function when t is less than pi over 2. I just started that at t equals 0. Since for Laplace transforms, we're really just doing that on the domain of t greater than or equal to 0 anyway. And then for the second function that's shown in blue here, that's what I have for t equals pi over 2 and after. And so notice that I have a behavior change in what the solution is doing after that impulse function hits at t equals pi over 2. All right, so try some homework like this.